Right, so you guys can like watch me on here, or you can watch me up there, either one, right? In this day of television, it'd probably be, you're like, I'm watching TV, right? When I watch it on the phone, it seems more exciting. All right, so we went over some properties last time, and here's the thing. This is where your note cards become really helpful, right? Because how many properties do we have on page number 96? We've got 8 listed out for us there. Addition property, subtraction property, multiplication property, right? We went through those last time. We did all of them except, did we do substitution property last time?
Yeah, we did.
We did do that? Okay, good. So we went through all 8. What we didn't mention, I guess, was the distributive property, right? There's still some properties from algebra that we need to remember are still around, and we can actually use these in some of our geometry problems. So like the distributive property says that B times B plus C equals AB plus B plus AC, right? So that's the distributive property. These are the kind of things that you're going to be using in your proofs as we start doing proofs in the class. And so remembering what all of these things are called and what all of them represent, at least initially, that's not going to come immediately to mind, right? The more that you use them, the more the easier it's going to be to remember what all of these are called. So these 8 properties and the distributive property and some of the properties of equality that we're going to look at today, you're going to want to write those down on your card as we begin to do these proofs, so that you can recall those and you can write the correct thing down in your proof. Okay? So that's why I'm just being so generous and saying you can use a card. All right? That's why you guys, I should be your favorite teacher. Mm-hmm. Bottom line, right? Favorite teacher, right? Teacher of the Year award, right? All right. Let's see. Let's solve something. Let's solve 5x minus 18. 5x minus 18 equals 3x plus 2. And so what they ask us to do is to solve this problem. When we say solve, if I give you something like that and I say solve it, what am I asking you to do? Solve for what?
X.
For x, right? I'm trying to get x on one side and everything else on the other side. And so we're going to solve for x just like we would normally solve for x. But you need to tell me why you were able to do that based on the properties that we learned at the beginning of the chapter. All right? So the first thing that we're going to do is we're going to get the, they move the x term over the 3x over to the left side so that we've got x's all on one side. So they rewrite it as 2x minus 18 equals 2, right? So what did we actually do in order to do that?
Subtract.
We subtracted, right? You just got to yell it out. They don't wait, man. They don't, they're going to just take it, all right? So she's exactly right, and what we write down is the subtraction property. We use the subtraction property to do that. What did we subtract?
3x.
We took the 3x here, right? And we said we subtracted 3x from this side and we subtracted 3x from that side. So that's why we use the subtraction property to do that. All right? So the next thing we're going to do is we want to move our 18 over to the other side, right? And so what do we have to do to get our 18 over here?
Add.
Addition property.
We're addition. I like it. I saw what you did there, Cal. He's like, I'm going to say it loud and clear, and there will be no doubt that I know it's the addition property. Good. That's the Georgia Tech man right there. So that's how we get the 20 on the other side. So the last step, somebody else that hasn't said anything. Come on, Aiden. You were being so polite before. What's the next step, Aiden?
Division property.
The division property, because we're going to divide both sides by 2, and that will give us x equals 10. So this is the division property, right? So this is stuff that we've done before, but these are the kind of things that we're going to do whenever we start doing proofs, right? When I give you a problem and say, hey, this is what I'm telling you up front, this is what I'm giving you, and I need you to prove to me that this is also true, you're going to start going through steps like this and listing out properties and theorems and say, this is how we go from that beginning statement to that ending statement. Okay? And this is why, I don't know if you guys remember, but at the very beginning of the year, we listened to that John Piper, Pastor Piper's response to that 8-year-old kid. This is why he thought this was fun, because it was kind of like a puzzle for him to kind of figure out how the pieces fit together to get that outcome, you know. And most people either love this or they despise it. But we're going to try to make it at least fun enough to where you can tolerate it, not despise it, you know. I'll tolerate it. All right, so we could do some more. You know, 55Z. Here was another one, 55Z. Is it 55? Yeah, 55Z minus. Let's see. Wait a minute. 55Z minus 3, 9Z plus 12 equals negative 64. Right? So if we do this one here, first thing we want to do is
do the parentheses.
distribute it, right? Who said that? All right.
Yeah.
I think Camille got that one in, right? So 55Z minus, we're just distributing this 3 through this entire problem, everything in parentheses here. So 27Z plus 36. Nope, minus 36 equals negative 64. So that was the distributive property. And there's, you know, some of these things we can do in a different order than they do it in the book. We don't have to do it exactly the same way. The next thing, I'm assuming they combine like terms. Yep. And so they just said simplify for this piece, right? So they rewrote 55Z minus 27Z to be 28Z minus 36 equals negative 64. We just simplified there. We want to remove the negative 36 over. So somebody else that hasn't given an answer yet, Gabe?
28Z equals negative 28.
And how did you do that? What property? What did you do to get to that?
Substitution? No.
What were you, how did that negative 64 turn into a negative 28?
Oh, you divided?
No? What did you do?
Oh, you subtracted.
You subtracted, you really added, because it's already negative over here, so you took the 36 and you added that 36 to that 64, right? You did take a difference between the two, but because it was negative on this side, this is the addition property. You guys see that? We had to add a 36 to both sides to get negative 28. All right, so now, someone else, what do we have to do to get Z?
Division property.
Division property, I like it. And that is Z equals negative 1. See, now all I can, because I told you you look like my friend Jessica, all I can think of is Jessica. Your name is that Caitlin, is it? What is it?
Kylie.
Kylie. It does start with a K though,
Mm-hmm.
right? Is it K-I-L-E-Y?
K-Y-L-E.
K-Y-L-I-E, that's right, yeah, okay. I should have never said you look like Jessica in Louisiana. That's gonna mess me up. All right, everybody follow that? You see how you would use those properties to get that answer. All right, we're not gonna do the using properties in real life. We're gonna move on to some next properties so that we can get through all the material today. And that's at the top of page 98. If you want to see these. This is properties of equality. All right. So we have they're all under the general heading of properties of equality. So because they're properties, when I write down reflexive here, you know, if you were to write this down on a proof, you would say the reflexive property, right? That's what you would put down. So the reflexive property, it applies to both segments and it applies to angles, as all of these properties do here. So I'm just going to put segments and angles at the top and just say for AB, then we could say AB equals AB. Now, I know that seems really dumb, right? Of course, duh, AB equals AB. Why does that matter? And it's really hard at this point, and I probably spent more time racking my brain with this one trying to tell you guys why this matters because it's hard to grasp until we start doing some of these proofs. You got a suggestion, Aid?
I was gonna say for the proofs, it helps to prove that.
Yeah.
If it's a real number, then we can say that it can be equal to itself.
Yep. Right. Well, one of the things that we'll do in proofs is we'll say whether or not two triangles are congruent to one another, and we can prove that in various ways. And so I might have a triangle that looks like this, and two triangles are formed by it. Right. And so I've got a point A, B, C, D, and that we're proving that ABC, triangle ABC, is congruent with triangle ACD. And so in order to prove that, one of the ways that we prove it is we're identifying that this line segment there that forms one of the sides of triangle ABC also forms one of the sides of triangle ACD, and that line segment is equal to itself, right? And so it would be the reflexive property where we could say that AC equals AC. So that would give us the ability to say this line, the length of this line here is the same for both triangles. All right, so that's kind of that's the easiest one that maybe that makes sense to you. But you'll see as we start doing proofs where reflexive property comes into play. Like I said, we can say the same thing for angles. So for angle A, we can say that the measure of angle A, for angle A, sorry, I should have put a comma. The measure of angle A equals the measure of angle A. All right? So that's the reflexive property. The symmetric property says, if we're talking about line segments, we can say if AB equals CD, then we can also say that then CD equals AB. We can just flip those around, right? And then if we're using angles, we would say if my hands would only write what my brain is thinking, it would be done a lot sooner. If the measure of angle A equals the measure of angle B, then we can flip it around and say then the measure of angle B equals the measure of angle A, right? So we can write those in any order. I know why I'm writing messing up is from lack of chicken nuggets. So the transitive property is the last one. So for this one, we have three different line segments, AB, CD, and EF. And so if the first line segment is equal to the second, and the second line segment is equal to the third, then we can say that the first and the third are also equal to one another, right? That's all that statement's saying.
Couldn't you just say all of them are equal?
You could. But again, this becomes useful when you're doing some of the proofs that you say it like that, all right? And we're going to see this not only applying to segments and angles, we'll see it applying to some other things. And so anytime you see reflexive, symmetric, and transitive, they always mean the same thing. If you can prove that the first one is equal to the second and prove that the second is equal to the third, then you can say the first and the third are equal to one another. All right? But on your cheat sheet, if you want to just write it down like that, then that's fine, as long as you recognize that, you know, what that means overall. So we could also say if measure of angle A equals the measure of angle B, and the measure of angle B equals the measure of angle C, then we know that the measure of angle A equals the measure of angle C. We have an example in the book. That gives a line segment like this. And it says A, B, and then C, D. And they tell us that AB equals CD, okay? And they want us to show that AC equals BD. Okay? So this length here equals this length here. How can we say that is so if we know that AB equals CD? All right, so we need to write a proof for that. So let's walk through the steps. We always, when we're doing our proofs, we always start with what's been given. Okay, so we could start with the fact that AB equals CD. That piece is given. All right, and I'm gonna write this with, I'm gonna number these because we're gonna learn in the next chapter. I think it's the next section. Yeah, but this is what we call a 2-column proof, where we number them and we put our reason for each of the statements that we're making. On the left here, we put our reason out to the right, okay? So first of all, we know that AB is equal to CD, so that's been given. Again, now we're going to have to go back to something that we've learned previously, which is the addition property of equality. The addition property of equality. That's actually, that's what we learned at the beginning of the chapter, right? The addition property of equality. And the addition property of equality, the reason we're using that one is because that property tells us that if I add something to one side of an equality, I can add the same thing to the other side and they'll still be equal, right? And so for this one here, what we're adding to both sides is BC. So AB plus BC, we can say that that equals, and they write it in this order here, that equals BC plus CD. All right, at this point, I just want you to kind of make sure you're following along with why I'm saying this property is the one I'm using to make the statement that I'm making. All right, so we've said if we add BC to both AB and CD, and BC is this amount here in the middle, then AB and CD, then this statement is still true, right? That's still an equality. Now we're going to use the segment addition postulate. Now for that one, that's not something we learned in this chapter, right? Where did we learn that? Somewhere in chapter 1, right? We're in section 2.4 now, and we're referring back to something that we learned in chapter 1. Let's see. Give me about 30 minutes, I'll find it. Not there. It might have been the very beginning, actually. All right, so the ruler postulate, segment addition postulate. It's in section 1.3, chapter 1, section 3. Right, there's a little box in the middle of the page there. Postulate, postulate 2, the segment addition postulate. So, we learned that back in chapter 1 and we can't forget it. That's my point, right? This is the kind of stuff that's going to have to go on your index card as you're building your index card, because you're going to continue to use these for proofs until it reaches a point in your mind that I know the name of this and I don't have to write it down. I don't have to take up space on my card, right? But until you get to that point, if you see a box like this, right? These boxes on the page, those are important. And that's the kind of stuff that I would make sure that I at least understand, if not also, somehow, some shorthand way, write that on my card. Because those are things that we're going to often use in our proofs. All right? So we're going to use the segment addition postulate now to say that AC is equal to AB plus BC. AC, this distance here, is equal to AB plus BC. Now, in your mind, if you're thinking, well, why did we even make that statement? Well, it's because that's what AB plus BC is what we have right here in this second statement that we made. And remember, what we're going for is we're trying to prove that AC equals BD. All right? So without looking at the book, if this is the direction that I went for statement 3 here, what do you think statement 4 is going to do? I'm watching you. Oh, I see you looking down, Jackson. Without looking at the book. If I use the segment addition postulate to take AB plus BC and say what it was equal to, what do you think I might be? Yes?
Are you going to do CD plus BC?
Yeah, so I wanted this portion here. Is that what you were going to say, AB?
Yeah.
Right? What am I going to set that equal to?
So BD is equal to BC plus CD.
Exactly. All right? So BD equals BC plus CD. So now I'm taking this portion of that statement there, and I'm using the segment addition postulate to make that statement. Can anybody say segment addition postulate 3 times really fast? I heard blah, blah, blah. Geometry, geometry, geometry. Blah, blah, blah. That was supposed to be a take on Cloudy with a Chance of Meatballs. You guys ever seen that movie?
Yes.
The mayor's like, I heard blah, 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 science, 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 blah, blah, blah. Bigger! And bigger is better. All right, so segment addition postulate. Now, I'm ready to make my final statement. And my final statement that I'm trying to prove is that AC is equal to BD. Right? Now, why can I say that? Because here I'm saying that AC is equal to, I said that AC by the segment addition postulate was equal to AB plus BC, which is what I have right here. And here I say by the segment addition postulate that BC plus CD is equal to BD, which is what I have right here. So that means I can say AC, which is what this is equal to BD, which is what this is. And so what did I use how was I able to plug this in for these terms here, and say they were equal to one another? Again, this is just something you have to be able to see. You should be thinking, well, you just substituted that in because the 2 were equal to one another. So it's the substitution property of equality, which is what we learned about at the beginning of the chapter, right? See, in section 2 here, we use the addition property to say that AB plus BC equals BC plus CD. But then in statement 3, I proved that this is the same as AC. And in statement 4, I proved that this is the same as BD. And so I could substitute these in for those guys and say that AC then is equal to BD. You guys see how I did that? Did I lose anybody? Want me to go through that magic one more time? Was it this class or the last class? So I said, nothing happens by magic. All right. So if you look at it and you go, I'm like, how did I do that? And you're like, magic. No, there's a way that we did it. So always ask me to explain the magic, right? How did we go from here to here? Does I need to go through this for anybody else one more time? You got it? You just raise your hand up like slightly. No? I don't know, does that mean? No? No? Okay. All right. Just playing back there. It's like here's the church, here's the steeple, right? Open it up. Oh, I did it wrong. Open it up, there's the people. You guys ever seen that?
Yeah, I see.
All right. Okay. So let's go on to, how are we doing on time? 1:30. We got 30 minutes. 30 minutes of sheer fun. Alright. Let's move on. I'm not going to do example 5 just because I'm afraid we won't have enough time. But it would be a good example to go through. So if we have enough time, remind me to go back and do example 5. Okay? From the last chapter. But let's move on to section 2.5. Proving statements about segments. Alright? So, we're gonna write down, this is theorem 2.1, and this is properties of segment congruence. Properties of segment congruence. And so there is a reflexive version of this. There is a symmetric version of this. And there's a transitive version of this. Does that sound familiar?
Yes, sir.
That's exactly what we had over here, right? So like I said, some of these things are going to be very similar, related to one another. But here the emphasis with this is that we're talking about congruency. Like I said, some of you struggled with that on the quiz. What does congruent mean? If I have two congruent line segments, Josh, what? Sorry.
They make the same angle.
They what? No, it's line segments. So I have two congruent line segments. They're the same length, right? So the measurement, if it was two congruent angles, you're right, the measurement of those angles would be the same, right? So we're really kind of stating the same thing that we're stating here for segments, but now we're going to talk about them in terms of congruency rather than equality. All right, so for any segment, for segment AB, we can say that line segment AB is congruent to itself. I'll replenish my energy while you guys are writing that down. Only one chicken nugget left. I hope I make it to the end of class. Now, I want you to see that what we're talking about here is we're talking about congruency versus equality. All right? And in essence, this is saying the same thing that this is saying. I wait till everybody's looking up here because some of you have no idea what I just pointed to. So I'll wait till everybody's done. All right? This is really saying basically the same thing as this, right? But this has the little equal with the little squiggly line, the tilde over it, right? Which means congruent. Line segment AB is congruent to line segment AB, where this is saying the measurement of line segment AB is equal to the measurement of of AB, of that segment. So one's talking about the equality of the measurements, the other's talking about the congruency of the line segment. Okay? So they're really talking about the same thing, but when you give proofs, you can't just jump from one to the other. Like if you're doing a proof, you may say something like, I know that maybe we know this. Let's actually, let me do the next one here. If AB is congruent with CD, then CD, we can say the reverse, and CD is congruent with AB. So again, one is saying that the measurement of these two are equal to one another, and you can write that in any order. The other statement is saying the two are congruent to one another, and I can write that in any order. And again, remember, if I write this, that means what?
Line AB.
Line segment AB. If I write this, what does that mean?
Just line. Or just AB.
It doesn't really.
I haven't heard the word I'm looking for yet. This means line segment AB. This means the measure of line segment AB. So that's the physical length. That's the physical distance. Okay? This just references the line segment, so that if I write AB on here, if I write that down, I know that you're talking about this line segment here. But if you write AB, now I know you're talking about what is this distance? What is that measurement? Okay? So it's just a way that we write. It's like the difference between angle A versus the measure of angle A. Right? If I've got this, and this is A, when I say angle A, I'm just talking about the angle that's right here. But when I talk about the measure of angle A, I'm actually talking about how many degrees is that, right? I'm talking about the 35 degrees or whatever that is is the measure of that angle, okay? So make sure you understand the difference. And when you're talking about the line segments, when you're talking about them being related to one another, you talk about them being congruent. But when you talk about the measurement of the length, you talk about those lengths being equal. Okay? So I just want to make sure that you get the difference between the two. One is the line segment, one's the measurement of the length of the line segment. One is the actual location, the angle as it exists in the diagram, the other is the actual measurement of that angle. Okay? So the transitive version of this, when we're talking about segment congruency, is if AB is congruent with CD and CD is congruent with EF, then we can also say AB is congruent with EF. I've got 20 more minutes and I've got to last on half a nugget. It's not going to happen. It's a good thing I got my chips. I've got a backup plan. Any questions about how these are similar. These statements are similar to this, but not exactly the same thing. This has to do with the measurement of the length, and those measurements being equal. That's why they're properties of equality. This has to do with congruency of the line segments, and that's why it's called the properties of segment congruence. So like if I measured line segment AB, and I found out that line segment AB was equal to 5 inches, this would not be true. Because this is not a measurement. Alright? This AB without the line refers to the measurement of length. So that I would say was equal to 5 inches. Okay? Yes?
So basically, the top one, the line segment AB, you can't really like use that in your problem. It's pretty much just referencing the segment.
Exactly. Yeah. It's just pointing to that segment in the diagram or whatever, right? Okay. So let's do an example, and they give us. This is example 1 on page 102. They give us 2 line segments. And one is XY, and one is PQ. And what we have given is PQ, line segment PQ, is congruent with line segment XY. And they want us to prove that XY is congruent with PQ, with line segment PQ. This is the symmetric property of congruence. All right, they're asking us to prove that. Right, this is what the symmetric property of segment congruence tells us, that we can write it like this, but prove it. All right, so let's try to prove it. And this will kind of give you an idea of how these proofs work as we get to more complicated problems. So again, I'm going to have my statements. This is what we call a 2-column proof. So I've got my statements and I've got my reasons. All right. So this is a 2-column proof. If I ask you for a 2-column proof, that's what I'm asking you for. I want you to draw it like that, right? And you're going to label your statements numerically. You're going to write statement 1, and then give me the reason for each of those statements.
So is statements always on the left and reasons always on the right?
Yep.
So it's never switched for a 2-column proof?
Nope,
Okay.
it'll always be that way. Okay, so like I said, we always start with the given. And sometimes we have multiple givens, and so we may not start with every given, but we at least start with a given when we're writing our statements. And so the given is this. In this case, we only have the 1, so that's the only thing that's given. And so this is where the measurement versus congruency comes into play. Because I know that PQ is congruent with XY, then I can say that, because I know that segment PQ is congruent with segment XY, then I can say that the measure of PQ is equal to the measure of XY. And the reason I can say that is because this is what the definition of congruent segments tells us. By definition, congruency means that if 2 segments are congruent, their measurements are equal. All right? So this is just because of the definition of congruency. And again, that was something we learned back in chapter 1, probably right there very close to the beginning, if not in the very beginning section. We were using rays and lines, and yeah, it wasn't in the very beginning, but it was probably around 1.3 or 1.4. But we defined what congruency was, and congruency means that the measurement of the two is equal. All right? So do you guys understand that? Cool? Now we can also say, then if this is true, we can say that if we reverse the order of their measurements, that this is also true. And we just learned this today. So what property would that be that tells us that?
The reflect. Nope. That's one of the.
So there's two. There's the reflexive. There's three things: reflexive, symmetric, and transitive. Which one counts?
Symmetric.
Symmetric, right? And you can kind of, one thing that'll help you remember that is when you talk about symmetry in a figure, is that you can like flip it around an axis and it looks the same. So like in pre-calc, we're learning that for a parabola, there's always an axis of symmetry. And if you flip it around that, you reflect it around that, it looks the same. So that may help you remember that it's the reflexive property. David?
So couldn't you just use the reflexive?
I'm sorry, not reflexive, the symmetric property. What now?
Couldn't you just use the symmetric property as a reason to prove that?
No.
Because it's
No. What we're proving right now is we're proving the symmetric property of congruency. All right? We're proving what we just learned in theorem 2.1. So we're proving that we can make that second statement in theorem 2.1, and we're basing our proof on what we learned in the last chapter when we talk about properties of equality. And so what we learned in the last chapter was that if these are equal to one another, then you can flip it around and say that these are equal to one another.
got it.
All right? But that's a good question. Because I want to make sure that questions are going to help with this, make sure that everybody understands it. So now that I've been able to flip them around based on the symmetric property of equality, then I can say that means that this line segment is congruent with this line segment. I can write that in that order. And again, the reason why is because of the definition of congruent segments. The definition of congruency says that if you tell me the measurement of two segments are the same, then I can also say that those two segments are congruent with one another. Any questions about that? I'm going to look each of you in the eyes. Do you have any questions? And I'll know. I'll know if you do. You're stuck at this. Piper won't even make eye contact. She's like, I won't look. I won't know. No, seriously, do you guys have any questions? A lot of times if I give you something long on a quiz or a test, I'm not going to ask you to just do the whole thing. I'll kind of do a portion of it, like we're going to do on a problem here, this next problem, and I'll leave blanks and you have to fill in the blank. All right, so I'll kind of give you a guideline for how the proof is to be laid out, and then you just have to fill in the blanks for that. Again, best teacher of the year award. All right. I like it. I can't wait to receive that award. I'm going to prepare my speech right now. So in addition to two column proofs, we also have paragraph proofs. And I'm not going to write all that out, but you can see at the bottom of the page, the proof that we just did as a two column proof, you just write it out as a paragraph, right? You say you are given that PQ is congruent with XY. Segment PQ is congruent with XY. We can say by the definition of congruent segments that the length PQ is equal to the length XY. Right? Just write them all as sentences and write it out as a paragraph. I don't like paragraph proofs as much, so you may be asked to do that just to make sure that you can take this and write it out as words, in a paragraph. But most of the time, this is what I'm going to be asking you to do, is do the 2 column proofs. Yes?
Why does it take so long to find the proof? Because if it says like PQ is congruent X, Y, isn't it just already given the same?
Yeah.
Now we can do this.
Yeah.
Well, so in the future we can use this because we have that as part of theorem 2.1. But they're just asking us to prove that theorem 2.1 was true. And so that's why we did this proof, right? A lot of times in math, they will tell you that you can say that this is equal to this or whatever. But we don't like you to just take that information and believe us and run with it. We like to show you why that's true. And so that's what we were doing here. We were just showing you why property number 2, the symmetric property in theorem 2.1, is true. And so we just worked that out. All right. But now that you know that that's true going forward, you can say the symmetric property of segment congruency says that I can go directly from here to here. All right, and I can skip over those middle steps. All right, let's do another example. And this example has some blanks in it. And so we're given a triangle that looks like this. And we've got points J, K, and L listed there. And we're given that LK is equal to 5. What is LK?
5.
Huh? It is 5, but what does LK represent?
Measurement of the line segment.
The measure of the line segment LK, right? That's crucial. I want that light bulb to come on. That doesn't mean line segment LK, it means the measure of line segment LK. Okay? LK equals 5, JK equals 5. So we're talking about the physical length, and then the line segment JK is congruent with line segment JL. So we're given that. And we need to prove that LK is congruent with JL. So if JK is congruent with JK is congruent with JL right here, then prove that LK has to be congruent with JL. All right? And so here's my 2-column proof, statements with my reasons. We're going to put some blanks in there. We're going to say blank is given. We're going to say another blank is given. And point 3 is going to be that LK, the measure of segment LK, is equal to the measure of segment JK. And we're going to say that's the transitive property of equality. I'm going to abbreviate some of this instead of writing out property, just prop. 4 is LK, line segment LK is congruent with JK, line segment JK, and you need to tell me the reason why that is so. JK is congruent, JK is congruent with, line segment JK is congruent with line segment JL. And that's given. And so finally, we have our final statement 6, and we're going to use the transitive property of congruence to prove that. All right. Now, let's see. So, I told you we always start with a given, but we may not start with all of our givens. So here we've got a given that's down near the bottom. But since that one's JK and JL are congruent, those line segments, what does 1 and 2 need to be?
LK equals 5 and JK equals 5?
Yeah, it's just the other two, right, that are given. LK equals 5, JK equals 5, right? Everybody would have gotten that on a quiz, correct? All right, so that was given to us. We can say that the LK and JK, that those measurements are equal to one another, and that's the transitive property of equality. Why is that the transitive property of equality? That's that thing that always says, you know, if A equals B and B equals C, then we can say that A equals C. That's the transitive property. So why would that be how we go from here, to the given to there? Let me write it like this. LK equals 5, 5 equals JK, LK equals JK. Do you guys see that? If LK is equal to 5, and 5 is equal to JK, then I can say these two are equal to one another. Alright? That's why they use the transitive property for that. Alright, then how do I go from this, the measurement of LK is equal to the measurement of JK, and say that means that these line segments are congruent with one another? Cal?
Definition of congruence.
Definition of congruency. Commit that one to memory because this one's going to come up a lot. Definition of congruency. Alright? Tells us that if the measurements are equal to one another, then the segments are congruent with one another. Now, we use our other given statement that JK is congruent with JL. And so based on that, we're going to use the transitive property of congruency, not the transitive property of equality this time, but the transitive property of congruency. Remember that one said if segment AB is congruent with BC and segment BC is congruent with DE, then I can say that segment AB is congruent with DE. So what's going to go right here? Somebody that hasn't said anything yet. Brittany.
LK, line segment LK is congruent with line segment JK.
Line segment LK is congruent with line segment what?
JK.
That's what we say right here. So what must it be? It's not line segment JK is congruent with JK.
JL.
LK is congruent with JK because we've already said that, but it's the next one, right? It's JL. So almost there. Close enough to get your name here. Just in the nick of time. And that's what we were trying to prove, right? So that's our final statement that we were trying to prove. Everybody follow that?
Yes, sir.
All right, there's another one. There's another example in the book. I would recommend going through that using segment relationships to prove one more. But that should give you enough information to complete the homework. All right, you guys have a good day.
You too.
Thank you.